So can you tell me a little bit more about axions and kind of make the case? I've looked at axions myself, but just kind of
Yeah.
I'd kind of like to hear from one of the major people in the field. What's the strongest case you think for looking for the axion particle?
Okay. Well, the so-called standard model or core theory has been just enormously successful. No clear discrepancy has been found from it, even though it makes very precise predictions for literally thousands of experiments, and people have designed to try to disprove it or push its limits, so it's been tested in very extreme conditions now, but there are a couple of things that are incompleteness of the theory or aesthetic flaws of the theory that are quite striking when you look at it deeply. So we should look at it deeply. It's close to the last word, I think, in physics. And one of the striking aesthetic flaws is that there's a parameter in the theory, something called the theta parameter, that a priori has a value between minus pi and pi. So it could be any within the theory. It's just a number in that range. But experimentally, turns out to be, well, we haven't seen a deviation from zero, but it's certainly less than 10 to the minus 10. So that would be quite a coincidence if that you just have a number that's otherwise unconstrained and it happens to be so small. So we suspect there's a principle involved, and the number has a very interesting qualitative meaning. Its most striking consequence, if it were not zero, is that it would give a new source of violation of. It would give a new source for violation of time reversal symmetry. So this amazing fact that the laws of physics, the basic laws, the microscopic fundamental laws, when you run them, if you run them backwards in time, have exactly the same form. So if you took a movie on a self-contained process, so we're not talking about big things where it's complicated because the second law of thermodynamics and so forth, but it's really small things where you can actually see the basic equations at work. If you take a movie of it and work it and run it backwards, it looks like a legitimate movie. You can't tell that it's been run backwards. Almost. There are some tiny obscure effects in the decays of elementary particles that are not quite that way. So it's really annoying explaining why it's not exactly a fundamental principle, but almost why. And we have a very complete story that would be completed if we could understand why that darn number, that theta parameter, is as small as it is. That would really that would really tie up a beautiful story in physics where we now would understand why time reversal symmetry is almost but not quite realized in nature. So that, and then in the late 1970s, Roberto Peccei and Helen Quinn put forward some ideas that could address this question. They introduced something called Peccei-Quinn symmetry, and if you implement this symmetry, then it explains why this parameter is so small. It could explain. Now, that was very important work, but they failed to notice two things. that was where I come in. Well, I mean, actually, it's a little more complicated, but basically, because I didn't know about their work at first, but the two things they didn't notice are, first of all, that their proposal implies a potentially observable consequence and a dramatic one, it necessitates the existence of a very light, very weakly interacting particle. So a particle with quite novel properties in compared to the particles we know about. And so I realized that, and that's the axion. I named it the axion. There's a little story with that. I had wanted to name something axion, a particle an axion, for quite a while. I guess I was in my early 20s at that time, but when I was in college, I went shopping with my mother one time and noticed this detergent up on the shelves called Axion, and I said to myself, if I ever get a chance to name a particle, I'll name it Axion, because it sounds like a particle. It's really nice. It's like, it's like pion, muon, axion, and it's Greek, so it's Greek. It's ion, and so then when it turned out that this particle is connected to an axial symmetry, it turns out that really, so the stars were aligned, and I had a chance to name something axion. And it also cleans up a problem. So since the detergent, the stars were really aligned. Anyway, so I did. So pointing out the existence of this particle was one of the things that was missing, and then the other thing that was missing only really became clear 2 or 3 years later, which was the way the theory had been analyzed, both by Peche and Quinn and by me and by Steve Weinberg, who did similar work to what I did independently. By the way, he originally wanted to call the particle a Higglet. So I saved the world from Higgslets, which is one of my great contributions, I feel. He graciously agreed to call it axion. The other thing so the thing that we all did, which is kind of what people did at that time without much thinking about it, was minimize a potential. So assume that the world is in its lowest energy state. And when you do that when you minimize the potential, it's minimized at theta, very close to zero. And that's how the theory works. However, that's wrong. I mean, that's inadequate. Because the world does not simply, that's not the way the world works. It doesn't get a command from on high, minimize the potential. We understand the universe is a dynamic, has a history, a dynamics, and you really should work out the consequences of the equations in the context of that history. In particular, we now know a lot about physical cosmology. We didn't know so much then, but at that time, so that's one of the reasons why people did this default assumption, because they didn't know what else to do. But things were clarifying by the early 80s, and so I proposed that we should look at the cosmology of axions and how they get produced in the Big Bang, and so and then with John Preskill and Mark Wise, we analyzed that quantitatively and found a beautiful surprise that if you worked out how axions get produced in the early universe, they could solve a problem in cosmology that was emerging at that time, the so-called dark matter problem. Astronomers seem to have built up a strong case that they need a new particle that's very, very weakly interacting, and that forms a big fraction of the mass of the universe. In fact, it's roughly 6 times as much as the mass in conventional matter, like electrons and protons and the things we're made out of and the things you study in biology and all branches of engineering and chemistry. So axions, which were invented for a completely different purpose, just happen to also potentially provide the dark matter of the universe. And that's where we are today. We don't really know. We haven't yet. I mean, both the theory of axions in the sense of addressing this problem of why time reversal is approximately true but not exactly true, and the phenomenology of dark matter have really prospered in the intervening years. No competitive theory has emerged really in either case for the phenomena, and a wider range of phenomena has been studied, and all the theoretical arguments that we put forward have been very carefully vetted, and I don't think much is maybe tailored here and there a little bit, but really not changed much, and so there we are. So it's a very beautiful, or it's a very tantalizing situation that we have this convergence of different ideas that appear very solid, and now the task is to test them experimentally if we can. Axions have fairly well-defined properties up to one parameter. It's a one-parameter theory, basically. One parameter is still a lot, unfortunately, if you have to design different experiments for different values of the parameter. And the parameter can vary over several orders of magnitude, which is the situation. But people are rising to the occasion, and it's a very tantalizing process. It's also been very interesting from at a personal level, because for a long time, those of us who were Axion fans were kind of a voice in the wilderness. People thought the dark matter was something else, that these arguments were so recondite, so abstract and theoretical, and involved things like instantons and non-perturbative QCD, and the experimentalists didn't want to hear about that. They liked their WIMPs, and they were much more kind of tangible particles that were more like the things they were used to, and but as time has gone on, and we've persisted in the evangelizing and very vigorous searches for WIMPs, both at the LHC and in astronomy, many different means, and specialized detectors that were very sensitive. They've all come up empty, and the window hasn't completely closed, but a lot of the glamour and hope of WIMPs in the early that people had has faded, and axions are now expanding to fill the void. Now, it's funny, if you look at the citations for the early papers, they kind of dribbled along at a few per year, and now it's like a hockey stick that's risen. Where it's depending on the paper, there are many papers now that have hundreds or thousands, close to 1,000 citations per year. Well, several hundred for sure, maybe, and rising. So it's amazing. And I don't know how long that's sustainable without actually finding the particle that we can, and actually finding the particle that might go back down again eventually. But that's the situation now. It's very, very exciting.
I think it's interesting that you kind of consider yourself an outlier with working with axions for a long time, because sometimes even when I give talks about axions, people are still looking at me like, the soap? I have to explain.
Believe me, it used to be a lot worse. And, now there are regular international conferences, very well-attended ones on axions. Mm-hmm. As I said, but by physics standards, getting hundreds of citations per year for old papers is very rare. All right.
So there's a lot of talk about specifically the QCD axion, which you
yes,
said. But there's also axion-like particle search, like a lot of the time with looking for specifically only a dark matter candidate that doesn't necessarily solve the Peccei-Quinn symmetry. How do you feel about those experiments? I've always thought that those seem a little bit odd to be looking for in a parameter space that is not specifically in the QCD axion space.
Well, it's less promising for sure, because it's lacking one of the main motivations for it, and when you have theoretical proposals that introduce more parameters than you need to fit, it's kind of weak. So it's much better to have fewer parameters than and I would say that the theory of axions is basically a one-parameter theory, but it's solving very serious problems all at once, and so so the so-called QCD axion is very well motivated. Let me put it this way: is a much better way to put it. We can put it shortly. In the case of the QCD axion, if you don't find it, that's also very interesting. That'll have a big impact. In the case of these other things, if you don't find it, well, okay, that's life goes on, no big deal. But I'm happy to lend the name to other things, because these particles do have certain commonalities with the axion, typically. I mean, and people, I find it touching that people want to tap into the glory, the reputational glory of axions to use it as a label for their proposals, but yeah, I'm just babbling at this point, but yeah, that's it. It's worth, definitely we don't know what the dark matter is. It may be more than one thing, and exploring new regions of parameter space that haven't been explored is it's a spur to experiments, and you never surprises might turn up. So it's I don't want to discourage that kind of activity, but it's not comparable in my mind to looking for the actual axion. Oh, maybe in this line I should mention one more thing that's not speculative and has been actually quite fruitful. You can look for elementary particles, new elementary particles that have something in common with the axion. But another direction is to look for realizations of the basic ideas and equations of axion theory, but with different interpretation of the symbols and different values of the numbers, to find what I'd call emergent axions in material systems, in condensed matter. And that's been very fruitful. Very pretty stuff has come out of that. So those are axion-like emergent particles that are quite real. This is not cosmological speculation, but real experiments on real materials. Something called topological insulators is highly related to the equations of axion physics. In fact, I wrote a paper called Two Applications of Axion Electrodynamics, which basically anticipated a lot of the main properties of topological insulators already many years before they were discovered and became popular. So it's been a fruitful thing to think about. And in general, one of the nice things about axions is because they're different, they've inspired a lot of creative thoughts that won't necessarily result in discovering the actual axion or be relevant to the original problems it was meant to address, but are of interest in themselves. And got new kinds of experimental techniques, new kinds of emergent particles in condensed matter, new kinds of materials that people are exploring. It's been really having a tough, well-motivated problem for people to work on is a great thing.